Our last section for 6.2 is 6.2 HT for a hypothesis test. And so if n is large, then we can approximate the sampling distribution for a mean using a t-distribution with n-1 degrees of freedom. So we're going to say our point estimate minus our null value over the standard error, that is going to be approximated by a t-distribution with n-1 degrees of freedom. And we're going to approximate our standard error by s over the square root of n. So in section 6.1, we had to use a different formula to do a hypothesis test and a confidence interval. In 6.2, we use the same standard error formula for the confidence interval and the hypothesis test. And the way that we compute the p-value is we find the area of the distribution, the t-distribution, that's as extreme or more extreme than, not the null value, the observed value. All right, so you might remember the steps of hypothesis testing. We're going to state our hypotheses. We need to check our conditions. We're going to calculate the test statistic, compute a p-value, do a generic conclusion, and then interpret in context. So let's consider that same data set about runners, the Cherry Blossom 10-mile run. This time I took a slightly different random sample of 100 people. And what we want to do is assess whether the average age of the runners is significantly greater than 36 years old. In the sample that I took for this section, the mean age is 38.44, and the standard deviation is 9.83. So our first step is to state the hypotheses, the null hypothesis and the alternative hypothesis. I think you folks know that I always start with my alternative hypothesis, and it's going to be about a mean. So I need to use the parameter for a mean, which is mu. So my mu, I would think that it was interesting if the mu was greater than 36. And that means that the null hypothesis that's the boring thing that, you know, we're kind of secretly hoping doesn't happen, but it needs to fill the rest of the possibility space. That would be mu less than or equal to 36. So we've stated our hypotheses. Next thing we need to do is check our conditions. So we need to check if n is greater than or equal to 30 and 100 is greater than or equal to 30. So the conditions are met. So the next thing we need to do is calculate our test statistic. So that's our point estimate minus our null value over the standard error. And maybe I'll start on another page right now so that I don't have to squish this all in. So in this case, our point estimate is x bar. Our null value, I'm going to note by saying mu 0, and we're going to divide by the standard error, which is s over the square root of n. So we need our x bar, that's our observed mean. In this case, that was 38.44. Then we need our null value. So that's the number that appears in our hypotheses. That's the 36. And then we need s. That was 9.83 divided by the square root of n, and I remember that was 100. So let's see, we've got 2.44 over 0.983, and that turns out to be 2.48. All right, so that's our test statistic. So now the next thing we need to do is compute the p-value. I usually start by estimating my p-value, and I just draw myself a little picture. And I don't have facts memorized about the t distribution because I can't. It really varies based on the degrees of freedom. But I sort of think about if it was the normal distribution. So I'm going to say this is a normal distribution. And I wanted to have 95% in the middle and 2.5% in the tails. Then this would be negative 1.96 and 1.96. And then my test statistic would be like out here in the tail, 2.48. And so it would have a small p-value, and I would probably reject the null. So that's my guess, just based on knowing a little bit of something about the normal distribution, is that we're probably going to reject the null. The guess doesn't always turn out to be correct, especially if you have small sample sizes, because then the t-distribution is different. But let's figure it out for real using Statkey. All right, so I'm back at Statkey. I want the theoretical distributions, and I want the t-distribution. Again, it's going to ask me for my degrees of freedom, and it's 100 minus 1 is 99. And then here is my distribution. And I could just hit the right tail button to give me one tail, because this is a one-tailed test. And then I could put in, instead of 1.984, I could put in my test statistic that we just computed. And that test statistic was 2.48, okay? And so then it gives me my p-value 0.0074. So this is really finding the p-value in Statkey. But we've got our degrees of freedom, which are 99. We put in our test statistic, and then we found our p-value. So I'm just going to go back and write on my previous slide. So the p-value was 0.0074. Then I need to do a generic conclusion, and I'm going to reject the null because 0.0074 is less than 0.05. And then, so we've computed our p-value, we've found a generic conclusion. Our last step is to interpret in context, and I would say we have evidence to suggest the average age of runners is greater than 36 years. So that's in context. All right, I don't think I have a lot of final thoughts. You're still going to compute the standard error as s over the square root of n. You're going to use degrees of freedom equal to n minus 1. You need to find the p-value using the t distribution in Statkey.